Hey everyone, and welcome. In civil engineering, there's a real dividing line between being a good technician and being a true innovator. It's the moment you stop just watching things work and you start proactively testing them. So today, we are diving deep into the strategic tool that lets you cross that line: design of experiments, or DOE. So let's kick things off with a tough question. We all lean on our intuition, right? Our hard-won experience. But what if those very instincts are making us miss something huge? What if the way we've always tested materials isn't just a little inefficient? What if it's actively hiding critical flaws that could lead to some really costly, maybe even catastrophic, mistakes? All right, so here's our game plan. We're going to start by looking at the problem with guesswork, and then we'll unlock the real power of factorial design. We'll cover the 3 pillars you need for data you can actually trust, the huge difference between statistical and real-world significance, and how you take all this from a clean lab to a messy job site. And finally, we'll see why this is your new secret weapon. Okay, first up, let's dig into the common ways engineers have traditionally done their testing. Now, they feel pretty intuitive, sure, but a lot of them are built on a foundation that's, well, dangerously flawed. And wow, this table really lays it all out, doesn't it? The best guess method? That's basically a shot in the dark. The classic one factor at a time approach is just wildly inefficient. But look at that third column, interaction detection. Notice that for the one factor method, it says none. It has zero ability to see how variables work together. And that right there is where the real danger is hiding. And this really gets to the heart of it. This isn't just about saving a little time or money. The biggest risk is missing what the source material calls hidden interactions. I mean, imagine you're testing a new admixture, but you only test it at 1 water-cement ratio. You might decide it's totally useless, but what you missed is that at a different ratio, that same admixture is an absolute game changer. You've just made a massive decision based on incomplete, local data. Okay, so this is where the hero of our story really comes in. If the old ways are basically flying blind when it comes to these critical interactions, we obviously need a smarter approach, one that's specifically designed to see them. And here it is, factorial design. Instead of changing just one little thing at a time, you strategically change multiple variables all at once in a structured way. This is so much more efficient because every single test you run gives you information about every single factor and, this is the magic part, about how they all influence each other. And this visual just nails the difference. The old methods, they give you a blurry snapshot of one single road. A factorial design, though, gives you the full, high-res map of the entire city, showing you how all the roads connect, and lets you understand the whole system, not just one isolated piece of it. Let's make this super simple with the golf experiment idea. If you only test one factor at a time, you might test a new oversized driver and see no change in your golf score. Then you might test drinking a beer and see no change. You'd probably conclude that neither one matters. But a factorial design would test all 4 combos, and it would find that hidden interaction. The oversized driver only makes your performance tank when you've also had a beer. That's an interaction, and finding those is how we prevent all those unexplained failures. Okay, so we've got a really powerful strategy now, but how do we make sure the data we're getting is actually trustworthy and not just, random noise? Well, that's where the 3 pillars of a valid experiment come into play. Now, these aren't just suggestions. They are like mathematical safeguards for your data. Randomization stops you from introducing bias, like, say, always testing one material in the morning when it's cold. Replication gives you a real feel for how much variability is naturally in your process. And blocking helps you isolate noise from things you can't control. For instance, if you treat each bag of cement as a separate block, you can cancel out the bag-to-bag variation from your final results. Without these 3, your conclusions are really just stories. Now, this brings us to a super important point, and it's a trap a lot of engineers fall into: confusing repeated measurements with true replication. Look, measuring the same concrete cylinder 3 times, that only tells you how precise your measuring tool is. It tests the gauge. Testing 3 different but otherwise identical cylinders, that's true replication. That tests your actual process. Getting this wrong can make you seriously underestimate your real-world risk, and that has massive safety and legal implications. So now we have data we can trust. The statistics tell us there is a real difference between material A and material B. But this is where the next and maybe most important question comes in. So what? What does that difference actually mean out there on a job site?
The source material gives a fantastic example. An analysis found a statistically significant difference in bond strength between two mortars. The difference was real, it wasn't a fluke. And the size of that difference? It was this: 0.28 kilograms force per square centimeter. Now that number works out to about a 1.6% drop in strength. Statistically, it's a real effect, but you, as the engineer, have to step back and ask, does it actually matter? If that new mortar is way cheaper, is a tiny 1.6% drop in strength a deal breaker, or is it a perfectly acceptable trade-off that you can easily design around?
And that is the definition of engineering significance. It's all about practical impact. A result can be statistically rock solid, meaning it's not due to random chance, but have absolutely zero engineering significance. At the end of the day, the real world of performance, safety, and cost is the ultimate judge of whether a difference truly matters. So the big question is, how do we connect all these dots? How do we take factorial design, statistical validity, and engineering significance from the clean, controlled world of the lab to the messy, uncontrolled reality of a construction site? And this right here is the ultimate test. It's one thing to prove a principle in a pristine lab. It's a whole other thing to make sure it's robust enough to work in the chaos of a real job site. This is where the rubber really meets the road. So 3 key practices really help bridge this gap. First, sticking to industry standards like ASTM C109, make sure everyone's playing by the same rules. Second, keeping your equipment strictly calibrated prevents measurement drift, where you think your material is failing when it's really just your sensor. And third, the whole goal of robust design is to find formulations that just don't care about the noise of the real world, like a swing in the ambient temperature. All right, let's bring this all home. This gets us to our final conclusion, the biggest takeaway from this whole thing. We really need to stop thinking of design of experiments as some chore we hand off to the statisticians and start seeing it for what it truly is. This quote from the source material just says it all perfectly. Design of experiments is not merely a statistical exercise. It is a strategic asset. It's not about math. It's about making smarter business decisions. Because when you use DOE the right way, you're not just getting better data. You are directly cutting your development time and your costs. You are minimizing your professional liability because you have a rigorous, defensible process. And at the end of the day, you're creating safer, more reliable, and way more innovative materials and structures. So, I'll leave you with this final thought to chew on. Think about your own work, the projects you're on. What are those nagging, unexplained problems that everyone just kind of accepts? How many of those are actually hidden interactions? Just like in that golf experiment, waiting for a structured, scientific approach to finally drag them out into the light.